Great. Welcome to the hottest seminar. In our second talk today, we're excited to have Evan Cavallo, who will tell us about cubes with one connection and relative elegance.
Thank you. So, this is joint work with Christian Sattler, and we're in the process of writing it up, so you can believe it when you see it. So I'd like to start off with a kind of one big picture that might help frame things. So there's this general expectation that models of homotopy type theory should correspond to some kind of infinity categories. It's not clear exactly what that kind should be, but I guess a recent big step forward towards this is Mike Schulman's proof that we can at least interpret homotopy type theory in any Grothendieck infinity one topos, which is some kind of infinity category. So it's a bit indirect, actually, what is meant by interpret here, at least what Mike means by interpret. When Mike says hot interprets in some infinity topos, what he means by definition is that actually we have some kind of one categorical presentation of this infinity categorical object. And then in a more fundamental way, hot is being interpreted in this one categorical presentation. So in Mike's case, sort of the content of his paper is showing that every one of these toposes can be interpreted by a certain model category, which has such nice properties that we can interpret hot in it. So in that case, the notion of one categorical presentation is a model category, although it could, in theory, be something else. And so, for example, the first model of type theory with univalence, Voevodsky's simplicial model, is sort of directly an interpretation of homotopy type theory in simplicial sets. And it happens that this interpretation makes use of and is somehow compatible with this model structure on simplicial sets, the Kan-Quillen model structure. And maybe specifically the thing here is that types are being interpreted as vibrations in this model structure. And that model structure is a presentation of the infinity category, the infinity topos of infinity groupoids, which we might call the infinity category of spaces. And so we have in an indirect way, an interpretation of hot in this infinity categorical object. And then another distinction that's useful to make here is between model structures and models of homotopy type theory. So, we have a direct sense of what a model of hot is. It's some kind of interpretation of the judgments of hot in such a way that we can validate the rules of hot. And this is not what a model structure is. A model structure is something coming from homotopy theory, but somehow there's this connection between these two things. So we're often talking about them being compatible with each other, but they aren't quite the same thing. So today I'm going to be talking mostly about cubical models of homotopy type theory. And the way we all ended up talking about these things was by asking the question of whether homotopy type theory has a constructive interpretation. And so now we know that the answer is yes. Actually has quite a few, or maybe various classes of them. And for the most part, these are all some kinds of cubical sets, or at least cubically structured things. And you'll forgive me for not spending all my time reading out the names. I'll let you read them. And a note to make here is that it was discovered that we could factor some of these interpretations through cubical type theories. So we could take some of the properties of cubical sets models and bring them back into type theory. And this gave us, for one thing, some higher dimensional type theories that have good computational properties that hot doesn't have. And maybe are also more practical for some kinds of arguments, if you like. And we can see there's like a quite straightforward translation from hot into these various cubical type theories, and then we can interpret those type theories in these cubical sets models. And as these things were originally written down in all these papers, they're interpretations of hot in, again, this direct sense of here's what this judgment means here, and here's how I interpret the rules. And however, it is the case that these cubical interpretations give rise to model structures. So in some work starting with Gambino and Sattler in 2017, and then kind of filled out in this preprint of Christian Sattler's equivalence extension property and model structures, the sort of corresponding model structures where the vibrations correspond to the types in these models were developed. And I and Anish Barbre and Andrew Swan did some work on another branch of these whole collection of cubical models, doing the model structure story for that. And Steve Audi has some notes also on this. So we do have these things. And they came out of these considerations of constructive interpretation and so on. And so when we were coming up with them, we didn't really think about what they presented. So now that's a question. What infinity categories do these model structures present? These are sort of new constructions. They're not exactly coming from classical homotopy theory. And so we don't have a theory available to say, what is this exactly? And a starter question maybe is, do any of these present the infinity category of infinity groupoids? Why want this? Well, it's sort of the most basic infinity topos. I don't know if that's quite right to say, but it's the infinity categorical situation that set has among toposes. So set is quite a basic fundamental topos, and infinity groupoid is the set of this infinity setting. And so one thing this would give us is a kind of constructive presentation of infinity groupoids. So not only these interpretations of hot, but also these model structure constructions are done constructively. Constructive. And here I should point out that there's also some work on doing this in a simplicial way. So the simplicial model structure, classical one as classically described, is inherently classical. There's a paper by Bezem, Kokan, and Parman about this. But you can fiddle with the definitions in such a way that you can make it constructive. And so I'll refer to these papers. I won't be talking about it here. And then another thing we might like is to interpret not just hot, but cubical type theories in infinity groupoids. And so there we would want some kind of cubical presentation. And ideally, that would be a springboard to get to interpretations of cubical type theories in other places. So sort of following the way Mike does things based on the simplicial model. So in order to start talking about cubical sets and so on, we got to talk about cube categories first. So I'm not going to give like a precise definition of what a cube category is, but just say things that are in common to the ones I'm talking about today. So the basic idea here is that our spaces are being built out of cubes. They're going to be presheaves on some category of cubes. And the category of cubes is going to be generated by products of some kind of interval object. So we have this object I'm calling I, and this object has two endpoints, the 0 of the interval and the 1 of the interval, which are maps from some object that will be terminal in our cases. And so for cubical type theorists and people who are interested in these questions, these products of the interval are usually Cartesian. And so in particular, we have some things fall out of that. So for one, this interval, we can collapse the interval to a point. There's this degeneracy map. That's not really specific to Cartesian cube categories. That's generally there. And then we also have this diagonal. So inside of the square, there's a diagonal. That's a bit more unusual. And we have symmetries. So we can rotate a cube by permuting its axes. And some of these are quite unusual from the perspective of classical homotopy theory. So the symmetries are a little weird, but it's really the diagonal that's strange here. So cubical sets go back a long time, about as long as simplicial sets go. But usually one has, say, the endpoints and degeneracies, but not these diagonals and symmetries. And maybe it's telling that the earliest cubical model doesn't have this diagonal, but for cubical type theory, we discovered it was cool to have it. Now, on top of these kind of basic things, you could have some extra toppings. So some that will play a role today are these connections. So I think it's easiest to think of these as binary operations on the interval, maybe as opposed to something to do with squares. So if you have 2 points on the interval, you could take the larger one or the smaller one and think of that as max and min operations. You could also have something that flips over the interval that sends 0 to 1 and 1 to 0 if you want. And I mean, you could, of course, invent whatever weird operations you want. And you also have, once you have all these operations, you have some choices about what laws you want for them. So for example, whether the max should distribute over the min and stuff like that. So we have this great zoo, and we're able to construct model structures for, say, let me stick to things that are Cartesian, and then whatever extra toppings you want, we could build something out of that. And so we could ask, do any of these give us model structures if we follow this Sattler construction that present infinity group voids? And so Ulrich Buchholz and Christian Sattler looked at this in 2018 and you can find a talk by Christian online, and there's some Google group discussion where Ulrich piped up. And so unfortunately, it turned out that none of them did, as far as we know. So if you just have the kind of minimal option of this original cubical model, which has faces, degeneracies, and permutations, you get something that is definitely not spaces. If you add in the diagonals, you still get something that's definitely not spaces. If you put in all this stuff and you have the laws of a De Morgan algebra on these things, you get something that's definitely not spaces. And these were the ones that kind of concretely came up when people were designing these cubical models. So they were the ones to look at. Then there's this really questionable one where you have distributive lattice laws for the two connections, but you don't have this reversal that you have in the De Morgan model. And we don't know what the story is for this one. And so as I'll get into a bit later, once you have this Cartesian structure, and it's really the combination of diagonals and connections that makes this cube category very nasty when it comes to like the tools we have from homotopy theory for analyzing these things. And I mean, the De Morgan one is equally nasty, but there's something obviously wrong with it. Whereas with the Dedekind one, we don't see anything wrong with it, but we just have no way to prove anything good about it. So I have no idea. I don't have a guess. But in the end, we found a model of HOT that was, or a cubical model of HOT that was compatible with a model structure presenting spaces. So in 2019, Steve Audi and I and Thierry Coquin and Emily Riel and Christian Sattler came up with this new model and model structure, which is again in presheaves over this Cartesian cube category, but where the model structure has been modified a bit. So there's fibrations, which are one part of the definition of a model structure, and this has a slightly different definition of fibrations. And if you remember in the model of type theory story, the fibrations correspond to what we're interpreting types as. And so it's the same cube category as before, but with a stronger lifting condition on the types. So that's cool. And now what I'm talking about today is the second one. So what Christian and I discovered is that if you take the 2 points on the interval, the degeneracy, the diagonal permutations, and just one of the 2 connections, then you also get, doing the original sort of Sattler model construction, not putting in equivariance, you get a model structure that presents spaces. And so comparing this to the equivariant model we already have, it's a little easier to describe. So again, we can just do the thing that we've already got on the shelf. But it's not that equivariance is gone in this model. Actually, the truth is that equivariance is there. It's just that once you have this Cartesian structure and the connection, all fibrations are automatically equivariant fibrations. So you could see this construction as an instance of the equivariant model structure construction as well. It's just that you don't have to, and so you can save yourself some wrangling. And the other thing is that the proof we know that this one presents infinity groupoids is more direct than the proof we know for the equivariant one. So that's a bit nice as well. But it's not my intention to fight against the equivariant model. What I would like is to have a general understanding of, you know, you give me a cube category and maybe you tell me something about how you want to do fibrations, and I can tell you, does this present spaces, or even like if it doesn't, what does it present? Can I give you a description of it? My hope is that someday we'll have a general understanding of these things. And this result is certainly not that, but it's maybe a small step on the way. Okay, so I'm definitely not going to have time to give you a full picture of this proof of ours. If you want to see sort of the first half of it, there's this preprint of Christian's called Idempotent Completion of Cubes in Posets. And there's a paper of Thomas Stricker and Jonathan Weinberger, which is a similar story. This is for the cube category with two connections, basically going as far as we know how to go for that cube category. And that part of the proof for us is more or less the same. So if you want some idea, you can look there. And the Striker and Weinberger paper also has some discussion of what's bad about the Dedekind cube category, if you want to see that. And so I just want to give some idea of what properties of the disjunctive cubes are important here for our proof. And so the bad news about this cube category is that it's not some good kind of thing called an elegant Reedy category. And this is the same problem that we have in the case with two connections. But what's good about it is that it's very close to being such an elegant Reedy category. And this is where it is different from the category with two connections, and how we're able to make progress here when we still don't know how to in the two connection case. So let me give you a quick introduction to, or sketch introduction to Reedy categories. And this is Reedy categories from a certain particular perspective of what we're trying to do. There's lots of other things you can do with them. But if we're thinking of presheaves on some base category C as spaces built from cells that are shaped like the objects of C, so built out of cubes or built out of simplices or whatever, it's useful if these two things are satisfied. So one, that we can stratify the objects of the category by some kind of dimension. So in the case of cubes, we have like the one cube that we think of being one-dimensional and the two cube that's two-dimensional and so on. And we have a similar kind of thing with simplices. And then whenever we have a map between two of these objects, we can factor them into some kind of degeneracy-like map that lowers the dimension, followed by some kind of face-like map that raises the dimension. So in simplices, for example, we can factor any map between simplices as first as one that collapses some stuff and brings us down to a lower dimensional simplex, and then include that as a face in this codomain simplex. And so because we're looking at cube categories that have isomorphisms in them, these permutations, what we actually want is something called the notion of generalized Reedy category, which was invented by Berger and Mordijk in 2011. And so there's some cutoff definition here, but the idea is basically what I've written above, that we have some kind of way of assigning degrees to objects, and then there's some kind of factorization system that matches up with the degrees in the sense that we factor through things of lower degree. And so the simplex category is an example. Some cube categories are examples, so the BCH one and the Cartesian one, and the ones that appear in classical homotopy theory mainly. And there are lots of other examples that don't exactly look like these ones. And for what's useful about Reedy categories for us is that if we have any presheaf over a Reedy category, then we can describe it as built up by sort of iteratively attaching cells of increasing degree. So we can start with the points of the presheaf, the things, its value at zero-dimensional things, so like the points in a cubical set, and then we could attach the one-dimensional things, the lines, and then the two-dimensional things, the squares. And at each step, this added stuff can be described as a push out of some, what I'll call a cell map, which is gluing on a bunch of n-dimensional things along their n-1 dimensional boundaries. And now we come to this notion of elegance. So this is an additional condition on a Reedy category, which I'll define, or at least give a cutoff definition of in a second. And so if R satisfies this elegance property, then these maps, cell maps, and then consequently the maps between these increasingly built up skeleta are monomorphisms. And the why this matters for us is that we're going to be looking at model structures where the cofibrations are the monomorphisms. And in this case, these colimits by which we can build up X are actually also homotopy colimits. So what I mean by that The colimits in our model structure are these sort of one categorical colimits. But if we think of the model structure as presenting an infinity category, then we also have, or may have, colimits in that infinity category in an infinity colimit sense. And so in this very nice case, those two things coincide. So these things that may in general just be one categorical colimits in our model structure actually present colimits in the infinity category. And we'll see why that's nice in a second, but let me give you that definition of elegance. So a Reedy category is elegant, and so this appears as Eilenberg-Zilber category in Berger and Mordijk's paper, and then as elegance in Bergner-Esque's paper with slightly different definitions that I'm kind of glossing over the differences between. So there are these two conditions, which I'll give an example of in a second, but the two conditions are, first, any span of degeneracy maps has a pushout, and any presheaf over the category, which is a functor from R up to set, sends those pushouts to pullbacks. And an alternative characterization of this second condition is that the Yoneda embedding preserves these pushouts. Okay, so how can I think about these conditions? Well, let's look at cubes because I like cubes. Cartesian cubes are an elegant Reedy category, so this will be a picture that works out here. Let's look at the 2 cube. There are at least two degeneracies I could write from the 2 cube. And let me look at the 2 where I squash the 2 cube along one axis and I squash the 2 cube along the other axis. So these are two degeneracy maps out of the 2 cube. And so the first condition in the definition of elegance is saying that this span has a pushout in the cube category. And in this case, the pushout of that span is the 0 cube, so just the terminal object in the cube category. And so the idea here is that whenever I have 2 degeneracies with the same domain, they have a kind of universal combined degeneracy. So the combination of squashing the 2 axes of the 2 cube is to squash the square entirely. And so then I would get down to a 0 cube. And then this condition on the presheaves is saying, or that the Yoneda lemma Yoneda embedding preserves this pushout square, is saying that I have this universal property with respect to any presheaf. And so the effect of that is if I have a square living in X, which happens to be degenerate along both axes, then it's actually degenerate in this combination. It's just a point in X. So that's the intuition of that. And so what did we want to do with all this? Well, what we're trying to do is build some kind of infinity categorical equivalence between our model structure on this cube category and our kind of standard thing, namely this classical model structure on simplicial sets, which we know presents infinity groupoids. And it happens that we have this adjunction between them. And it happens, in fact, that both of these are what's called the left Quillen adjoints. And so you should think of this as kind of a homotopical version of left adjoints. And in the same way that left adjoints in the one categorical sense commute with colimits, these commute with homotopy colimits. And so if we knew that everything in, say, our presheaves over the cube category was built up via homotopy colimits from some kind of basic cells, then to check that these round trips are inverses to each other in a homotopical sense, we would just have to check it on those basic cells. And then we would get everything else by this preservation property. And we can do that for one round trip because the simplex category is elegant Reedy. But we can't do it for the other round trip because this cube category is not. But I said that this cube category was kind of nice. So let's see how that is. So here were my generating maps of this disjunctive cube category. We have those max connections. And so like other Cartesian cube categories, it's a Lavoisier theory, which is just to say that it's a finite product category where the objects are all products of some specific one, here the interval. And therefore we can think of the maps in this category as terms in some theory. And it happens that we have a nice description of the theory here. So it's the theory of bounded semilattices, bounded both below and above. There's the theory. And so the maps here are maps from I to the m to I to the n can be written as n tuples of terms that vary in m variables in this language. But maybe more useful for us right now is that there's also an embedding from this cube category into the category of not necessarily bounded semilattices. And we embed the n cube as the semilattice, which has two things in it, one of which is less than the other to the power n. And for those who know about these kind of duality things, it will make sense to you that we can get this embedding out of a duality between bounded and non-bounded semilattices, or finite ones anyway. And so first, well, the bad news, disjunctive cubes are not Reedy, as I already said. And so here's an example of a bad map. This is the map from the 3 cube to the 3 cube, which I'm writing in this kind of Levier theory term way. That's sending the 3 coordinates x, y, z on the 3 cube to x, the max of x and y, max of y and z, max of z and x. And what does this, if this is our 3 cube, what does the image of this thing supposedly look like? It looks like this. And so this is a map from the 3 cube to the 3 cube, which is not an isomorphism, but it doesn't factor through a lower degree cube, which is a kind of thing that we must have in a Reedy category. So either something should be an isomorphism or it should factor through something of lower degree. But it can't factor through the 2 cube because it has too many points in it. And I chose this example to kind of prove something greater than I'm saying that it's proving. So what one should really be looking at is the idempotent completion of this cube category. And this is a map that doesn't factor there either. But that's for people who will know what it is. But what's good, we know that this cube category embeds in a Reedy category. And the one that I want to work with here is the category of finite semilattices that are also inhabited, which is the same as those that have a top element. And it follows that this is a Reedy category from sort of general properties of algebraic categories. You have a surjective mono factorization system. And so the idea is to borrow the cellular decomposition that we have in presheaves over this larger Reedy category to get cellular decompositions in the smaller cube category. So this embedding induces, and in particular, an adjoint pair. So if we start with a presheave over the cube category, we can turn it into a presheave over the larger category, break it down there, and then map it back. And this I upper star preserves co-limits, so we do get a description of X as a co-limit of some things. Okay, but to use this decomposition the way we wanted to, we need this kind of nice situation where the co-limits are homotopy co-limits, so we want those cell maps to be monomorphisms. And our larger Reedy category isn't elegant either. So not all presheaves or preheaves in this category have good decompositions. But, and here's the concept of relative elegance from the title, it's elegant relative to this inclusion. So any presheaf in the image of I lower star has a good decomposition. And so there's our definition. In the situation where we embed some small category in a larger Reedy category, we say it's relatively elegant when in R you have these pushouts of degeneracy maps, and just for things in the image of this I lower star, you get this pushout preservation condition. And this translates to having the nerve of this embedding preserve those pushouts. And so we show that if you have one of these things, then presheaves over the smaller category do have good decompositions where the basic cells are sort of a bit larger than you would have if you just had an elegant Reedy category to start with. And the relative elegance of this thing, like the existence of the Reedy structure here, we also managed to get from some general properties of algebraic categories. And it's easy to kind of check things on the basic cells, and I clearly don't have time to talk about that. So then we have what we need to finish our proof. So in the end, we actually have an adjoint triple here, and it turns out that both of these adjunctions are Quillen equivalences between our model structure and the one on simplicial sets, and in particular, our model structure presents infinity groupoids. And for those who know what a test model structure is, it's also the same as that. So I think I'll stop there. Yeah, it's I think one small step on the way to figuring out what is going on in this homotopy theoretically in this picture that came in an interesting way out of type theory. Thanks.
Great. Thank you, Evan. Silent applause. Any quick questions?
I have one, of course, but I'll let someone else go first if they have one. I had the first one last time.
Okay, maybe I'll go first then. Is it easy to, or can you say anything about what these cell shapes are that you're inheriting from the larger elegant-ish Reedy category?
Yeah, I mean, I don't know how to like describe them in a nice way exactly. So like in a formal, I can give you a formal description, which is they're things in the image of the nerve of the embedding quotiented by automorphism groups, basically. So it's the same picture you would get in the elegant case, but instead of representables, you have things in the image of the nerve. But I don't have in mind like any, like in this particular case, what do they in fact look like? That I didn't sit down and think about.
Okay, I've got one. The Kan-Quillen model structure on simplicial sets is not constructive, as you said. The cubical one is constructive. Is there something in the proof that's this proof that's not constructive that would understand that mismatch?
Yes, so there's a lot in this proof that's non-constructive, at least in the sense that we can think of some specific things that are non-constructive, and also we haven't been careful at all. So there are probably many things we're doing that are non-constructive. But I mean, an interesting question here is whether anything. So there are some questions now that we can ask whether they have constructive answers. So one question is, are the equivariant model structure and this one constructively equivalent? So we know they're equivalent now by combining the comparison through simplicial sets. But there we can define them both constructively, but we don't know if they're equivalent constructively. And we also have these constructive versions of the simplicial model structure, so we can ask whether those things hold constructively. There's one thing that definitely doesn't hold constructively, so I had an extra slide that I didn't go into. That was one of the questions, but one of these Quillen equivalences is definitely not constructively valid because the cofibrations are more restricted in the constructive simplicial model structure. So they're not just the monomorphisms, but they're the level-wise decidable monomorphisms. And so one of the left Quillen adjoints stops preserving cofibrations, and that breaks it. And then the other one, we don't know.
Okay, very interesting. Thanks.
Okay, so let's thank Evan again.